So in this video we will go over how to do the post-lab for experiment 10, estimating an electrode potential. This is the data I received from doing the experiment. Your data may vary because of many different factors. Maybe the bromine water was a little more fresh, or maybe I did not heat it long enough. If you notice here, the sodium nitrate was blue-green, and maybe if I heated it longer I would have gotten the transition that I was looking for, which was bluish. So there's many different factors here. So this is the data that I have, and you can use your data to follow along because once again your data may be slightly different than my data. So the first step, what we wanted to do was take VO2 plus 1 and see which one of these reagents, which one of these 5 reagents will reduce this. When it gets reduced, the product will be VO plus 2, and that means that will turn from a yellow color, this is yellow, to a blue color. Well, when that gets reduced, these guys, if the reaction were to happen, would get oxidized. So right here we're looking for a yellow to blue transition, and you noticed really we had 2 of them. I should have probably included this one in my post-lab calculations, but and I think if I let it heat it long enough, it would have totally turned blue. But we're looking for SO3 minus 2 and oxalic acid as being the ones that really catalyze the plus 5 to the plus 4 state. Okay, and same thing here, the gist of this experiment, we're doing the opposite. The blue to yellow transition is an oxidation. Which one of these will oxidize VO, this time plus 2, to VO2 plus, and as this gets oxidized, each of these will get reduced. Remember, an oxidation and a reduction must happen as a couple. So a blue to yellow transition, and I only got 1 of them. Again, your data may be different because the reagents may be different, particularly the bromine water. The bromine water may change from stock to stock. Preparation of the VO plus 2, the equation is actually given to us. All we need to do is calculate the stoichiometry of that reaction. The stoichiometry of that reaction is shown right here. So here, when you prepare the VO plus 2, we're going to take 15 mLs of that. This is already in the acid, and we will, according to this equation, add some sodium sulfite. And the sodium sulfite, this is the solvent, so there's the acid, and that's going to react with the sodium sulfite, and that's going to give you sulfate, and that's going to give you the blue VO plus 2. So 15 mLs of the 0.05 molar, and following the stoichiometry here, and then a 10-fold excess will make it 0.47 grams. So adding a whole bunch of the sodium sulfite will make sure that this reaction moves towards the VO plus 2, giving you the blue, so that you can test the blue to yellow transition with all these different types of chemicals. So adding an excess is totally okay because according to Le Chatelier's, it's going to shift it to more of the products. We want to get rid of any of the excess sulfate or any of the excess SO2 gas through some heating. So our first pre-lab question is, what electrode potential will you estimate in this experiment? And this is the pre-lab, so this is something that we should already have been well prepared for. We're trying to find X here. Okay, this is from our PDF PowerPoint, and the idea here is that we want this as narrow as possible. Okay, we cannot get a single number. It would be great if we could get a single number. We just can't. What we can do is get a range, and we want our range to be as close as possible. Okay, so the window that's most narrow, more than likely the correct answer is within here. You see, if your window's this far, the answer could be, anywhere from here to here. But if your window's here, more narrow, the answer's within this tight space. So the narrower the range, the better this experiment goes, and the better you'll have confidence in reporting that value of X. But we're reporting a range. We're not reporting an actual number. So we'll make this estimate by testing a series of reagents, right? So if we go back to here, our data table, we're testing each of these. Okay, so which one of these can get oxidized and in turn reduce this will give us one, side of the range, and which one of these reagents that gets reduced and in turn helps oxidize this will be the other side of the range. All right, let's look at pre-lab number 2 here. Calculate E cell for the following reactions. So remember, we're determining a range here, so we're not looking for a very specific number. Okay. First thing I want you to recognize is that if I were to label this A and label that B, A is one reaction, B is the other reaction, but it's been flipped. So B is nothing more than A that has been flipped. So if we get E cell for A, which is some range, all we need to do is inverse or flip that to get the E cell for this part B reaction. So for the first pre-lab question here, they want to get the E cell in terms of X. Okay, so this X here that we are interested in finding. So first thing is we have Br2 going to 2Br. So let's go ahead and deconvolute that. Okay, we have 2Br going to 2Br. This is minus 2. So I'll balance it out with electrons, with 2 electrons there. This has a this is a reduction reaction, gain electrons reduction. So it gained 2 electrons. Cathode is where reduction happens. And looking at our lab, this is 1.07 volts. So this is the cathode. We'll call that 1.07 volts, which means that VO plus 2 going to 2VO2 plus has to be an anode, because a cathode will react with an anode. But you can see here this X is a cathode reaction, so we'll flip it. When we flip it, this becomes a minus X. Okay, so let's flip this reaction. And instead of calling this X, because we flipped the reaction, we'll call it minus X. Okay, so I'll multiply this anode half reaction by 2, realizing that this still becomes minus X. Okay, you multiply this by 3, that's still going to be 1.07. We're just multiplying the bottom half reaction by 2 to cancel out the electrons. Okay? So when we do that, when we cancel out the electrons, our net oxidation reduction reaction is basically that above. The only difference is that I wrote it in terms of H+. They wrote it in terms of H3O+. That's why you have the discrepancy in the waters. 1.07 minus X. Okay, we add 2 reactions, we add their corresponding anodes and cathodes together. So E cell is going to be 1.07 minus X. So if this were a positive reaction, if this reaction, were to go forward, then this would be greater than 0, right? Because a positive voltage is the only reaction that's going to favor the products. In electrochemistry, a negative voltage for a reaction will not favor the products. It's just simply a reaction that will not go. So for this reaction to proceed, then we can move this around, and we'll find that X, I'll move this X to the other side, X will have to be less than 1.07 volts. Okay, that is the condition or the criteria for this reaction to proceed. You can test this. You'll put like 1.06, which is less than 1.07. Plug 1.06 here, and you'll get a positive voltage. Negative voltage won't go. Reaction will not proceed. Okay, the reaction here is just a flip of the top reaction. So if we're going to flip the top reaction, now this becomes the anode, and that makes it minus 1.07 volts. Now this is no longer the cathode but the anode, and this gets flipped. That becomes the cathode instead of the anode, and this becomes plus X. Okay, so this, for the second reaction, the flip reaction to occur, it's going to be minus 1.07 volts plus X. That must be greater than 0. All right, some of these other pre-lab questions are pretty much self-explanatory. If no immediate reaction occurs, you've done this in the lab, and you saw in the demo, we add heat to spur the formation of the blue to yellow color change or the yellow to blue color change. What are the colors of the individual ions and the oxidation state? All of that is found right here in the PDF of the PowerPoint. We should know what the yellow oxidation state is. We should know what the blue oxidation state is. The combination means you have a little bit of the +5 and +4. We usually want to switch it one to the other color through heat. And this last stuff here is stuff that you can get from the protocol. We usually prepare this with sodium sulfite, and we heat it to get rid of any SO2 gas. So all of that pre-lab questions, as stated before, is found in the PDF. So let's take a very quick look at the post-lab questions. Looking at our data, which resulted in the reduction of the VO2 plus ions, and here we're looking at a yellow to blue transition. This is kind of a back and forth. You can probably also include NaNO2 here. So in my observations, I would also include this as causing the reduction of VO2 plus to VO plus 2. So in my calculations, it was SO3 minus 2, NO2 minus, as well as oxalic acid. So let's go ahead and do sodium sulfite first. This is my data. Your data may be a little bit different. So let's look at our table here, and it's going to be right here in our lab handout, okay, for this one. So this actually is reduction. So we're going to flip this, because this flipped is oxidation, and that oxidation caused this reduction. All right, so we're going to take this reaction and flip it, make it the anode, and make this an oxidation reaction. All right, so this is going to be, actually this is going to be minus 0.17 volts. Since I flipped that reaction, I will flip the sign. And this is oxidation, I lost 2 electrons. Reduction, so now we will do this as the reduction reaction, keeping it as X. So I'm actually going to, instead of doing H+, I'm going to do H3O+. That's just making this with the H3O+ even. So that actually makes this 2 H3O+, plus E minus, and that goes to VO plus 2 plus 3 H2O. Okay, and this is a reduction reaction. This is the reduction reaction, gaining 1 electron. That's going to be X. Okay. So the only difference here, this half reaction and this half reaction, is that I made this 2 H3O plus, and because of that, instead of 1 water to balance the equation, the hydrogens and oxygens, that becomes 3 waters. Okay. So this is our anode, that is our cathode. Let's cancel out the electrons. In order to cancel out the electrons, I'm going to multiply this one by 2, that becomes 4, 2, and this becomes 6. The reason why I do that, this still remains X. The reason why I do that is to get the electrons to cancel out. And now my net oxidation reduction reaction is 2VO2 plus H2SO3. These 4 H3O pluses cancel, so I'm happy about that. Also, these waters cancel, so I'm happy about that. And that's in an equilibrium with 2 VO plus 2 plus SO4 minus 2, and there's a water that's in there as well. So I think this is balanced. I'm pretty sure it is 5 oxygens. 4 plus 3 is 7 oxygens, 2 plus 6, 7 oxygens, the 2V, 2V, 2 hydrogens, and I think we're balanced. Plus 2 plus 4 minus 2 is plus 2. So 0.17 volts plus X. Now this reaction facilitated the reduction. We got the yellow to blue transition. So I'm going to go ahead and say, because this reaction got the blue change, it's going to be minus 0.17 volts plus X is going to be greater than 0. And that means X here is going to be greater than 0.17 volts. All right, so oxalic acid gets oxidized. So let's see the oxalic acid here. It gets oxidized. So I think what I'm going to do is flip this. Okay, I'm going to flip this. And this gets flipped, and let's go ahead and write that in its flipped form. And so here we gained 1 electron, so that is like before the cathode, gaining electrons. And here we lost 2 electrons, oxidation, so this would be the anode. All right, I'm going to multiply the top one by 2 to cancel out my electrons. So that makes it 4, this makes it 4, and that makes it 6. This still remains X. Now I could add these up together. And then the 2 electrons and the 2 electrons cancel. 2 of these H3O pluses cancel out with 2 of these H3O pluses. And 2 of these waters cancels out, leaving 4 of these waters. And now let's write our net reaction. Our net reaction is going to be 2 VO2 plus H2C2O4 plus 2 H3O plus. That's going to give us 2 CO2 plus 4 VO plus 2, VO and plus 2 at the top, and I'm getting 4 waters. Okay, we add the 2 reactions, we add the cathode and the anode together, so this is going to be X plus 0.49 volts. This has to be greater than 0, right? Because this reaction, according to our data, facilitated the reduction. We got that blue to yellow transition, if you remember. So here, X is going to be greater than, moving it to the other side, minus 0.49 volts. So that's one range. So pretty wide range. If I were to draw this on a number line, here's my 0, here's minus 0.49 volts, here is 0.17 volts. Okay, so far we know this magical value of X must lie somewhere within here. Okay, hopefully we can get a little bit more narrow and narrow and narrow. Close the window. So the last substance that caused the reduction of VO2 plus to the plus 2 form was sodium nitrite in acid. So we can take that half reaction, which is here, we flip it to make it oxidation. That's minus 0.94 volts. And I already went ahead and wrote the half reaction for the cathode, gain electrons, and anode, lose the 2 electrons. I'm going to multiply this top half reaction by 2, so that makes it 2. And this is 4 H3O plus 2 electrons, and 2, and this makes it 6. And let's see what can cancel out. So adding the cathode and the anode together, we have successfully canceled out our electrons, so our net is going to be 2 VO2 plus plus 4 H2O, which should cancel with that H2O, plus HNO2, and plus 4 H3O plus, which should cancel with that H3O plus, and that's going to give us 2 VO plus 2 plus NO3 minus plus 6 H2O plus 3 H3O plus. Okay. So let's just clean up some of this. It's a little messy. Well, the 2 electrons cancels, which is a good thing. Some of the waters will cancel out, and then one of the H3O pluses will cancel out. And then let's go ahead and write the net for this, and then remnant 2 H2O. H2O is everywhere, so it's really not that important. And so we add the 2 reactions, and then that means we add the 2 half reactions, so X plus a minus 0.94 is going to be plus into minus is minus, so X minus 0.94. Since this reaction went all the way, the X minus 0.94 volts should be greater than 0, and here we have an X value that's going to be greater than 0.94 volts. You can actually put a value of X here, and X that's 0.95. Okay, put 0.95 here, you'll get a positive voltage. So let's look at our 3 one more time. So of the 3 that successfully reduced this, X greater than 0.17, X greater than minus 0.49, x greater than minus 0.49. And then we just realized x is going to be greater than 0.94, which is all the way here, 0.95. So really didn't get a narrow window here. The only thing that we could definitively say, is that x is probably, since is going to be greater than 0.94 voltage. And that's our answer for the post-lab, determining which one reduced VO2 plus to VO plus 2. Now we got to do the same thing, looking for those reagents that oxidized it, going the other way. Okay, looking at my data here, the only one that really successfully oxidized VO plus 2 to VO2 plus was the hydrogen peroxide. Okay, so everything else remained blue. We're looking at the second part of the experiment, and the only thing that did it was H2O2. So when this gets oxidized, this H2O2 gets reduced. So let's look at the reduction reaction for H2O2. Okay, so this is a reduction reaction, and cathode gaining electrons happens. Gaining of electrons happens at the cathode. So here the E cathode is 1.78 volts. And now what is the X here? Now remember, our X here is the oxidation, so we have to flip this. Okay, we have to flip it. When we flip it, this becomes minus X. Okay, when we flip it, this becomes minus X. So let's go ahead and flip this. And I'm going to give the version that has H3O plus. Okay, it's just because this version has H3O plus. Okay, so that is our E anode. Okay, I'm going to call that minus X, because we flipped it. Like before, I'm going to multiply this bottom half reaction by 2. So that becomes 2VO plus 2. This becomes 6. This becomes 2. This becomes 4. And that becomes 2. The 2 electrons cancel out with each other. And let's write our net reaction. Let's go ahead and cancel some of these, shall we? In my eye, I see that this 4 H2O will cancel with that 6 H2O, leaving me with 2 H2O. And this 2 protons will cancel out here, giving me a remainder of 2 protons. So H2O2 plus 2VO plus 2 plus 2 H2O. And that's going to give me 2VO2 plus 2 H3O plus, and this is going to be a cathode plus the anode. I add the 2 half reactions. We add the 2 to get the E cell. So the E cell here is going to be 1.78 minus X. Since this reaction went forward and we got the successful oxidation coupled with the reduction of hydrogen peroxide to water, the 1.78 minus X must be greater than 0. Okay. So with that, we will have X is going to be, and there we have it. We do have our limits now. Okay, on one end of the spectrum, we have 1.78, and on the other end of the spectrum, we had, if we look back at our notes, we had 0.94. So here's our range between 0.94 volts and 1.78 volts. X must be greater than 0.94 volts. X must be less than 1.78 volts. This is the window upon which we think this X lies upon. Here we have the X right at the center. We have the 1.78, okay, facing the number. And then right here, what we calculated from previously, the first post-lab question, here we have the caret facing the X. So the caret facing the X is right here. And this is our answer for the range. Okay. In the last post-lab questions, they ask you to calculate the mean. So we'll go ahead and calculate the mean of these, the mean of our limits. Here's one limit on one end. Here's the other limit on the other end. So let's go ahead and calculate the mean. And on my calculator, the mean, I found it to be about 1.36 volts. All right, our last post-lab problem. Here we're going to estimate our range, which was 0.94 to 1.78, that is our window. So it tells us to take the mean of these two limits as your crude estimate and use that for this reaction here. So this reaction is the cathode because it gains 4 electrons, and this reaction here, we'll flip it to make it oxidation in the anode. So let's go ahead and flip this reaction, realizing that when we flip it, it is not 1.36 volts, but it is minus 1.36 volts. And I'm going to change this so that the H plus is in the form of H3O plus, just to make it correspond to this. Alright, so I rewrote that equation, but this time I flipped it, and I just want to make sure I'm balanced. I am balanced. And this time this is a 4 electron transfer reaction. 4 electrons are being transferred. So I'm going to multiply the bottom by 4. So that makes this 4. This makes it 12. This makes it 4. This makes this 8. And this makes that 4. This stays at minus 1.36 volts. And the 4 and the 4 cancel. This is 12 waters. And looks like that's going to cancel, leaving me with 6 waters, and I have 8 protons here. That will cancel with some of those, leaving me with 4 protons over there. So let's write our net reaction here. Let's see here. We have 4VO2 plus the 4 electrons are gone, and 4H3O plus. Okay. So adding the 2 reactions, adding the anode and adding the cathode, we add these 2 together. So 1.23, this is going to be E cell, 1.23 plus a minus, so that's minus 1.36 volts. And what is that equal to? 1.23 minus 1.36 is a minus 0.13 volts. Okay. So yeah, that probably explains why it won't react with air, because this VO plus 2 does not have the oomph, does not have the power to reduce O2 to water. So the negative voltage for this electrochemical cell means that this reaction cannot occur, and VO plus 2 cannot react with oxygen to give you acid and VO2 plus. Why? Because the negative voltage tells us that this reaction does not favor the product side of the equation.